we will now look at the memory order consume and how that affects optimizing compilers. And we will see that they have to do significant analysis before doing any optimization, which otherwise can lead to weird code. Wrong code, actually. So we have this A carries a dependency to B, and the compiler is responsible for not optimizing away such dependencies. And if there is no dependence, it can reorder code. Okay, so if we start with an atomic load of Q with memory order consume, then the compiler has to create a dependence tree which starts with P as a root. So it will now check dependencies from P to expressions which use P, or something that is computed from P. Okay, so the effect of that is that this star P is not allowed to move to before the load, since there is a data dependence between that assignment and that use. So that clearly makes sense. But the consume allows the compiler to move this B to before the atomic load. This may, for instance, be in a loop, and this B may be allocated to register, so it doesn't have to be read from memory every time. So that's what expected and what we want. But now we will see an example which makes this somewhat problematic if it's not done very thoroughly, analyzed very thoroughly. Okay, so first something from optimizing compilers, constant propagation. That's basically a transformation which tries to compute values at compile time and use them instead of computing something that is known at compile time. I mean, it's no point in computing them at runtime if it's known at compile time. Okay, so, and this is a very trivial example, and constant propagation can do many interesting things. It was published in 1991 by IBM. Okay, I have to stop myself from talking about optimizing compilers, but I at least in this course, but we will see what can happen. So assume the compiler has determined that the value of size must be 1. Okay, then I mod 1 clearly is 0. Okay, so then we will access B of 0. Okay, and then B of 0, that's the same as star B. Well, it doesn't matter if it's B of 0 or star B, it's the same thing. But the important thing is that I is gone. And this dependency tree that the compiler created from a consume, it started with the I, and then when we use I, that expression is dependent on this I. But now the compiler has optimized away I. So the compiler would not see that it cannot move this read to before the consume. And that violates what the programmer possibly had planned. Okay? And what to do about it? Well, the compiler simply must analyze all such dependencies before modifying the code. And it also must preserve the dependencies And what does that mean? It means inserting special synchronization instructions so that the hardware doesn't reorder the instructions anyway. Okay, so now consume looks all of a sudden more complicated for compiler writers than first thought, perhaps. As a very first slow approximation of this is that the compiler can define consume to instead use acquire. Well, that's not what the programmer wanted, but during development of the compiler analysis for C11, it can be useful to start with using acquire instead of consume, since that will order the memory accesses. Okay, one more data dependence. What do we have here? Here we start with a consume. Then we will create the root of this dependence tree that makes this store dependent on the load. But this store is not dependent, so it can be moved to before the consume. Okay, so sometimes we can win performance or gain performance by using consume, but it is it is important to be very careful so that we really know what we are doing.